What was we talking about?
Solid state.
What was we talking about as part of solid state? Yeah, we're talking about diodes, but there's some we're talking about that's used in almost all electronic devices. Huh? Yeah, or power supply. And we're just on the very, very first part of a power supply. A power supply consists of multiple units. We're on a section referred to as the rectifiers. And basically, the rectifiers is not even the power supply. The rectifiers are a part of the power supply. So right now, as I get my PowerPoint up, and of course, when you know the network would be busy. So this is basically the makeup of a power supply. And we're going to add to this as we go along. So the first power supply we're looking at is a power supply we refer to as a unfiltered, unregulated power supply, which would be this guy right here. And then what we're going to do is we're going to add a filter. And we'll call that an unregulated filter power supply. And the very last thing we're going to add is what we call a regulator. So power supplies consist of what you need to run the piece of equipment that you're going to run. Of course, which one would be more expensive? Well, the bottom one would be more expensive than this one, right? You understand that? So why would I have a filtered regulated power supply to run just a DC motor? Odds are we would, because a DC motor don't need all that garbage. Now, if I was going to run a stereo amplifier, then we would have to have every bit of this, right? You understand that? So it depends on where we're at or what we need to run. So we came over here and we put together this little tiny power supply. So our power supply is not even like this. Our power supply is just a tiny bit more complicated, but not much. So we could do it this way. This would give us, if we bring 120 volts in, what DC would we get out? Well, first of all, I'm going to say 120 volts, right? You understand? And I'm going to figure VP. So I'm going to take 120 volts and I'm going to divide it by 0.707. And what do we get? So we got your calculator out first thing in this class, right? So what we got? What's that? 91 volts, or close to it. Now this one we wouldn't take out the 7/10 because why? We're over 100 volts, and 7/10 are not going to make much difference. Okay. So what I'm going to do now is I'm going to take this and I'm going to divide it by pi, 3.14. Yeah, it's supposed to be 170 volts. You multiplied, Joe, instead of dividing. I don't know, I should have caught that right off the bat. But if we're dividing by a fraction, yeah, it's about 170 volts. Yeah, I'm going to that'd be about 340 peak. 340 peak to peak. 340 peak to peak. I'm going to divide this by 3.14, and what do we got?
Roughly 54.
Okay. So anything that needed to run on roughly 54, we could run on the supply. Well, I'm sorry, any motor that could run on roughly 54, we would run. Right? You understand that? Does that make sense? And we didn't take out the 7/10 because we're well over 100 volts, right? And the 7/10 just don't make that much difference. If I don't want to run off Alabama Power, if I don't want 54 volts, we're going to put another device in there called a what? Starts with a T. Yeah, we're going to put a transformer. So transformers are what sets our output voltage. If we don't want to use line voltage, what we call line voltage, then we're going to use a transformer. And we're going to either do what with the transformer? We're going to step up or we're going to step down, right? You understand that? So this is what our power supplies are going to look like. We're going to start off with this. Then we're going to bring the 2 wires in to the transformer. And then we're going to come up here and we're going to bring it into a rectifier. And then we're going to take the output. So it depends on what you need, what components we're going to use in the power supply, right? You understand that? So this is because we're not going to deal with 54 volts. For one thing, 54 volts is over what they consider to be the lethal voltage. So we would run into problems. So that means we'd have to start considering other things besides safety glasses, right? You understand? So we're going to use very low voltage in this class, just like we normally do. Because we're going to be dealing with some unsafe. If we deal with higher voltage, we'd be dealing with something unsafe. So we're using what we call a 12.6 volt center tap transformer, which means we can get 2 voltages out of it. We can either get full secondary voltage or we can get 1/2 secondary voltage. And we're going to use the full thing. Now, when we're talking about this, we're talking about the output voltage, the center tap, right? You understand that? Everybody okay there? Any questions? So what we got is we got a transformer. It's rated at 110 volts, but we know we're not doing that, so that's what it's rated at. And it says at 110 volts over here on the center tap, over here on this side. I don't need to put the arrow there. If we came out all the way across it, so if I use both outside leads, we should get approximately 12.6. If we come across half of it, then we'll get 6.3. This is exactly what's on your house. Y'all understand that? So on your house, if you come around off the 2 outsides, you get what we call 240. If you come off between the center and the side, you get what we call 120. Now that's just what NEC calls it, but it's going to be a range inside there. Plus minus 10%, I believe, is what Alabama Power allows. So what we're going to do, and what the circuit that we have set up is pretty simple. So the circuit we have set up is we don't have that one. So the circuit we have set up, let me go ahead and put this in. So here on the PowerPoints, this is the secondary voltage, right? This is not Alabama Power. So this is the symbol we use for an AC voltage source. Well, for our circuit, the transformer is the voltage source. Right, you understand that? And if we wanted to get more complicated, we could trace it all the way back to the plant, but that's going to be a lot of transistors, a lot of transformers, a lot of substations. If we come up here and actually do the circuit, the complete circuit from Alabama Power to the transformer, then our circuit looks like this. We're not connecting anything to the center tap. We're coming over here. We got a diode. No, I'm sorry. We don't have it like that. And then we're using a resistor as the load. We're using a 1K resistor. What's the color code for a 1K resistor? And then right now we're using this common. Yeah, black red. So this is our circuit. And of course we could look at it and this is rated at 12.6 volts, but we understand that it's not going to be 12.6, it's going to be something around that, right? You understand? Because that 12.6 is rated at 110 volts on the primary at 1 amp. So if we don't pull 1 amp, we're going to get a little more than 12.6 volts. If we don't hook it up to 110, so it's all depending on that, but they're going to give you the rating on the transformer. Does that make sense? Okay. So what output should we expect? So first of all, we're going to calculate VP because these are RMS values, right? And I'm going to take 12.6 and I'm going to divide it by 0.707. What does that give us? Okay, 17.8 volts. Now that's peak. It's not peak to peak. But in power supplies, we don't need peak to peak, right? You understand that? All we need is peak. And then we're going to calculate something we're going to call V peak out, which is going to be on this side of the diode. So this is going to be equal to 17.8, and we're going to subtract the voltage drop of the diode. Okay, 0.7. Okay, so we say V peak out is equal to 17.1. And that's DC. That's not. Okay, then we need to calculate our DC. So our DC is going to be 17.1 divided by pi. Now the book don't teach pi, so this is the formula. So full wave, so DC full wave would be equal to 2 V peak over pi. Okay, you understand that? Huh? Yeah, but let's don't deal with that. So VP, right? Because when we use this formula right here, it wouldn't be any use, Larry, to use this one and multiply it by 2 just so I could drop the 2 over there. Understand what I'm saying? Okay. Okay. So DC full wave would be equal to the, we'll give y'all the same thing. Don't want to do that. So DC half wave is going to be equal to V peak over pi. Now the book comes up here and says we could take V peak and we could multiply it times 0.637. Now that's what the book teaches. There's a chart in there that shows y'all these ratios. Okay. But we're not dealing with full wave. So what we would have to do, this is for full wave, right? DC full wave. So if I was going to use this fraction, now all of a sudden I got to say DC half wave would be V peak times half of that. So now you got 2 fractions you got to remember in your mind, right? You understand? Yeah, but that's not what the book does. You can do a lot of things, but the book don't do that. You understand that? So the book gives you 1/2 of that because they're trying, and what I'm trying to say is that if I know 2 V peak over pi, so 2 V peak over pi to me is easy to remember. Y'all understand that? Because that basically comes right out of the radians formula, if y'all are familiar with that. So that means for full wave, 2 V peak over pi. For half wave, it's V peak over pi because it's 1/2 of the other one. Does that make sense? So instead of trying to come up here and memorize all these fractions, so doing this, we could multiply by 1.414. So the book teaches this. That says V peak would be equal to VRMS times 1.414. So now we got we've got 0.707, we got 1.414, we got all 0.637, we got all these fractions running around in our head, right? You understand? I understand what I'm saying. So as long as you don't cheat and copy off somebody's paper and look it up, if that's the way you see it, do it that way. But that's not going to be on the formula sheet. Y'all understand that? Yeah, but you can't calculate DC with RMS, and you're right. So I could go from RMS to VP by using 1.414, which is basically the reciprocal of this. So you can take a fraction and you can take a any division program and turn it into a multiplication program by taking the reciprocal of the divisor. Okay. And you're right, the meter would read RMS, but I don't use RMS to try to figure out what the DC output is supposed to do. We use what? We use VP. So you're right there. So what do we get here? V peak over pi, since it's half wave. Or 5.45 rounds up, so 5.5. And I think we measured 6.2, so that was within, 700 millivolts of what we calculated, just using what? Just using all the specifications that was given to us. So let me make sure I don't have anything shorted out. This transformer has a hum to it, which normally, if you hear a transformer humming at you real loud, then normally it means you need to turn it off instantly, because normally it means you got a short circuit or a short somewhere. But this transformer kind of misleads you. So we want to make sure we put our meter on volts. And what type of voltage are we measuring? DC. So we'll make sure we set up our meter to measure DC volts. Okay. So here's our circuit right here. Very, very simple. Here's the transformer. And I think I showed y'all the voltage rating and everything on top of it, right? Here's the 1K resistor, brown, black, red. Here's my diode right here. Okay. And we're going to come up here and measure the output. I've got an alligator clip. We call these alligator jumpers. I don't know if they carry them in the bookstore, but these guys here are real neat for this class. Now, you wouldn't use them in a 2,000 volt circuit, but they work out real well for this class. And we got our meter on DC. If you don't know what you're measuring, of course, you're supposed to start with the highest range possible, right? And as soon as I get my black leaf, red leaf pulled out, we're going to measure across. Oops. So it's measuring 6.5 volts. And it's measuring a negative 6.5 volts. Why is that? 6.05. Because it's a negative power supply. Now, how do I know it's a negative power supply? Well, when I look at my schematic, I see the cathode is pointing toward the source. So what you need to do is don't figure out current flow, just look at the diode. Y'all understand? So which way would current flow? Well, current's going to flow here. It's going to flow through here, right? It's going to make that minus, and it's going to do what? It's going to make that plus. So this is a positive supply. But the best thing to do is just look at the diode. If the cathodes are pointing toward the source, it's a negative supply. If the anodes are pointing toward the source, it's a positive supply. That makes sense? And of course, we came up here and we hooked up a motor to it. Oops, lost one of my. Now, what the DC polarity on a motor does is it determines the speed of rotation. That's what on a DC motor. So this is our common. We've established this as our common. Okay. And then I'm going to come up here and just put my motor across this. And something happened. I think I even put AC on it. I don't know what my motor's. Oh, I know it's not running. I'm off. So there's the motor. Runs great off of pulsating DC. So I'm just putting it in parallel with the resistor. If I put it on the AC, what did it do? Just sit there and vibrates. And come over and put it on DC, now it runs. Runs fine.
Okay, I'm a little confused. You turn down the rent,
What you're doing is you're trying to put the diode in an AC in a DC circuit. This is not a DC circuit. So what's happening is that my AC is coming in here. So the diode is going to be forward biased one of these alternations. It's just now it's forward biased on the negative alternation. Okay, you understand. I come up here and flip this around, all our calculations are going to be exactly the same. So what you're doing, Larry, you're seeing this in a DC circuit, but this is not in a DC circuit, it's in an AC circuit. And what happens is the AC changes polarity every alternation. So what we're doing is we're blocking one alternation and doing what? Letting the other one pass. So I'm going to come up here and turn this around. So now I'm pointing my, I'm doing this with power on, guys, but we're only dealing with 7 volts, right? So now when I come over here with my voltmeter and measure, if I can find my red lead, now it measures 6.05 volts, but now the negative sign's on it. So what's the diode doing now? Well, now it's blocking the negative alternation. It's letting the positive alternation come through and blocking the negative alternation. Now, if we knew what direction the motor was running a while ago, we would see now the motor's running in the opposite direction. So DC motors, the voltage polarity you put on the motor determines the direction of rotation. So DC motors are fairly easy to reverse. All we have to do is come up with some way we can electrically switch the leads. We do that usually with relays, which is pretty neat. Okay, so this is half-wave rectifier. Everybody okay? So, but I need a better DC. I want a more efficient DC that don't have that zero in there. So what we're going to do now is we're going to look at what we call a full wave rectifier. So yeah, that's it, 3.18. So I could calculate V peak if I knew 3.18. But like I said, 2 V peak over pi to me works on both situations. So we've already did this. Okay. Okay. And this is rule of thumb. When working with diode circuits, it is practical to overlook the effects of the barrier potential only when the peak value of the applied voltage is at least 100 times larger than the combined barrier potentials. So that means we got 7 volts. So 0.7, so 70 volts will be here. But in a minute, we're going to start putting multiple diodes in series with each other. This is out of the book, by the way. I don't forgot which figure it is. No, I think it'll work. So this is talking about a light. Of course, what here, the light is going to see RMS, right? So if this was 120 volts RMS, and I close the switch, when I close the switch, it's going to short out the diode. So now my AC flows around and goes through the load, right? So if this is 120 volts RMS, then the light bulb would light for 120 volts RMS. If I open the switch, Now it's got to flow through the diode. Now all of a sudden we have a half-wave rectifier, and we're only getting what over here? 54 volts, about half voltage, right? Isn't that what we calculated? So the light bulb would be about, would it be twice as bright? I hope people understand that. Remember, power varies with the square of the voltage. So if this was a 100-watt light bulb, and I put 120 volts on it, then I would be equal to P over V. So that's 100 watts divided by 120 volts. That's what the current would be. So what would the current be? Huh? Okay, 0.83 amps. So if I half the voltage, what's going to happen to the power in the lamp? The lamp's not going to give me 100 watts anymore, right? You understand? So what's going to happen to, so let's say we have it, which will make it easier right now. Huh? Well, we're trying to figure out what happened to the what? Yeah, that's the problem. If we lower the voltage, people think if we lower the voltage, we keep the same wattage. But that's not true. We're talking about the load. We're not talking about the source. We're talking about the load, right? You understand? So if we come over here and run this thing at 50 volts, so let's calculate R. So R would be equal, how do we calculate R? V. Okay, over I, so 0.83. So this is R. Now R is not going to change. So what we got? Okay, about 1.4K. Or 1.5K would probably be more correct. Okay, so 1.5K. Okay. So what I'm going to do is I'm going to calculate the power, and I'm going to use V squared. What's our voltage? 54 volts squared divided by R. V squared over R is the way we can calculate power. What's that? The 15K is right? Huh? Okay. Okay, thank you. That's okay. I was thinking say that can't be right. 153 ohms. That's okay, guys. Then we're going to divide this, because we was only getting 1 watt. I know it didn't drop down that much. 0.83 or 83 milliamps. 830 milliamps. What's that? Okay. 145? So V squared over 145 or about that. 54 squared, what we got? What's that? So look, we halved the voltage, so we went from 100 watts down to 20 watts. So some people take for granted that, okay, if I half the voltage, I can put that on a test, in any class. And they'll say, if I half the voltage, what happens to the power? And somebody, more than one's going to say the power will halve. The power varies with the square of the voltage. So if it goes up, it's the square. If it goes down, because the problem is that when we drop the voltage, what happens to the current? It goes down to the load, right? You understand that? And of course, power is equal to V times I. So if we half the voltage, we half the current. And the power would go by 1/4. If we double the voltage, we double the current. So power would go up by 4, right? You understand? So be careful on that. I'm going to put that on this test. And I make it a true false too. If I have the power to a volt, to the circuit, not people what gets what's going on inside the source and what's going on inside the circuit. Okay, y'all understand that? So if the output of the source goes up, the current in the load goes up unless I do something with the load. So this is what's going on. So what happens is a device that's designed to run off 240 volts is designed to run off 240. Y'all understand that? If I plug that device into 120 volts, it'll probably burn up, not because your motors won't start. They can't create enough torque, and the motors will probably burn up if you don't have an overload. So the load, once I set a voltage to the load, the current flow in the circuit is determined by the load, the voltage in the circuit and the load. But what we're trying to say is, how do I get that voltage there? So on transformers, if I'm trying to get 100 watts of power at 120 volts, but I use a transformer that goes from 1,000 volts down to 120 volts, 1,000 volts is going to be a lot less current in the source, right? You understand? But what sets the current in a circuit is the load and the voltage you put that load on. So this guy here would go from about 100 watts down to about 20 watts just by doing that, flipping that switch. This is something we talked about. The maximum reverse bias voltage that can be safely applied to a diode is what we'll refer to as the peak inverse voltage. Now, unfortunately, this is what textbooks usually teach. But when you look at the data sheet, they usually call this reverse repetitive. So it's VRRM. So when you're looking at it in the data sheets, this is going to be the mnemonic it uses, but it's going to put over there. So we're looking for the peak repetitive reverse voltage. And this is a peak voltage, not an RMS voltage. This is a peak voltage. So this is another reason you need to know how to take RMS and go to peak, right? You understand that? Because if you don't, if you got a diode that's rated at 120 volts and you put it into a 120 volts AC circuit, it's going to bop it. Because it's trying to block 170 volts, right? And this is what they're showing here. That's the peak. So we did that, negative. We looked at, that's the one we hooked up first. Are you okay there? All we do is do what? Look at the diode and figure which way it points. I can't reach over there anymore, move my table. If the cathode points toward the source, then it's a negative supply. If the anode points toward the source, it's a positive DC supply. Okay, so what we're fixing to do now is we're fixing to get into what we call a full wave rectifier, which means somehow we're going to guide that other alternation up to the top or to the bottom, depending on if it's a negative supply or a positive supply. The first one we're going to look at is what we refer to as, so this is what a full wave rectifier is going to do for us. We're going to bring our AC in through our AC source. It could be a transformer. And then when we go through the full wave, we're going to get both alternations up there. Are you okay? Now, the first one we're going to look at is what we refer to as, so what would be the output voltage here? And this is the wrong figure, by the way. I'm going to get rid of that right now while I'm looking at it. I thought I did this. So the book covers these, but they don't really cover you how to figure out what you're going to give out. So they go through all these different types of rectifiers. Now, the first one they look at is a for the full wave, just like we teach, is full wave center tap. So right now, I think we're working inside chapter 6. So what we'd use here, if you look at your formula sheet, then DC would be equal to V peak. What's V peak here? We don't have to use RMS. V peak is given to us. So this is going to be 2 V peak over pi, right? We're given V peak. So this should be equal to 30 volts divided by 3.14. Have I lost anybody? So I double V peak in my head, right? And what do we come up and get? Now, why are we using 2 V peak? So this guy here has an average of 2 V peak over pi. This guy here, but before, when we had half wave, this gave us a 0, right? You understand? When we average those two together, we come up with V peak over pi. But here, so this is the average of an alternation. 2 V peak over pi. 0.637. Which what they've done on that, of course, I showed y'all that, is they pulled the 2 V out, and then over pi times V peak. No. A cycle is one repetition of a repetitive waveform. Is this a repetitive waveform? Okay. So my AC coming in like this, let's say it's 60 cycles, and we was going to get into this later, but we might as well get into it right now. So here's my AC coming in, and then it's going to swap down, and then it's going to swap up. So my AC coming in, that would be one cycle. My DC coming out, there's a repetition, so there's one cycle, and here's one cycle. So on full wave, your output pulse frequency will always be twice as big as your input signal. So if this is 60 hertz, then these guys are going to be pulsing at 120 hertz. And hertz, by the way, has nothing to do with AC. Well, I'm sorry it does, but it also deals with what? It deals with anything that's moving in cycle, any electrical signal that's moving in cycles. So this is DC, but it's pulsing, but it's pulsing at a hertz, right? Y'all understand that? Yes or no? So yeah, good question. We're going to use a center tap full wave rectifier, and y'all need to know the name of these circuits. That's going to be on the first test, which I think comes up next Monday, right? And I went ahead and put the review up there. And what we'll do today is we'll give out a worksheet where y'all are going to solve from these rectifiers, these unfiltered rectifier circuits, and then we'll go over those Wednesday. The center tap full wave rectifier uses 2 diodes connected to the secondary of a center tap transformer. This only works with a center tap transformer. The main supply voltage is coupled through transformers to the secondary, of course. A transformer, of course, we know changes the level of AC voltages. It doesn't change power, it changes voltages, which causes it to change the level of AC current. Because when we're dealing with power, I is equal to P over V. And transformers don't change power. So power in and power out is the same. So this allows us to change the level of voltages, which is going to do what? It's going to change the level of current. Now, of course, what we're going to need this for is that normally when we deal with power, we put something that protects the power. So we got 2 options. We can put a fuse right here. Well, actually, we got 3 options. But the problem is, most people will want to rate the fuse for the secondary and not the primary. So the transformer will flat burn up. Right? You understand that? And the fuse will never blow because you're rating it for secondary current and not primary. The other option is to do this, which is the preferred method, but that costs another fuse. And of course, the third option is to do this, where you fuse the secondary and don't fuse the primary. And now the problem is here is you're not protecting the transformer. So the preferred method was to put a fuse in both your primary and your secondary. Most of the time you're going to find it in the primary only. So we'll figure out how to size that fuse. That's going to be pretty, how do we size that fuse? Everybody understand the primary. The primary is the one that's pointing back to the actual true source of the voltage. We call that the primary. All the primaries that's pointing toward the, let me find my blank. So when we come from Alabama Power, we're going to come from a lot of different voltage sources, right? So, you know, we come over here, we have Alabama Power, and then first thing they're going to do is they're going to run it through some transformers and step the voltage way up. And then they're going to run it through here, and then, you know, they might tap off here and come out and have some transformers right here. They might come over here to another set of transformers and step it sure enough way up. Depends on how far they're trying to take that power, right? You understand? Okay. These are these things we call substations. Y'all see these all over the place. And what's the function of those? Is it going to step it up for transmission or step it down for use? Well, every one of these have a set of transformers. And we're going to have two sets at least on a single phase. These guys right here are the primary, because these are pointing back toward the source. These on this side right here would be the secondary, because these are all pointing toward the what? Toward the load. At the college, we've got our own substation. It's a small one. It's over there by the Mill South building. Okay. So the secondary, the ratio between the primary and the secondary sets the voltage on the secondary. So you need to be able to take a ratio and figure out what the primary voltage would be. I mean, I'm sorry, the secondary voltage would be, or vice versa. And that's what this talks about here. Step-down transformers reduce the AC voltage to a load by a certain ratio, and step-up transformers increases the AC voltage to a load set by a ratio. So the ABB robot, the big FANUC robot over there, and the ABB robot runs on what we call 440. There's not 440 in this building. So what do we have to have? All we got is, we're not going to have a step down. The only thing available in this building is what we call 220 or 240 or 208 is what we have. So both those robots have step-up transformers. Yeah. The FANUC robot, when they installed that, it was installed first. So they put the transformer up in one of the electrical units upstairs, electrical rooms. The ABB transformer is on the floor over here. You see it over there. So this is a full wave center tap rectifier. And we have to use the center tap. So notice this is a positive supply. How do I know it's positive supply? Can somebody tell me? Yeah, because the anodes are pointing toward the source. Now, what you have to understand, by the way, these are polarity symbols. It depends on how the transformer's wound. A lot of times what they'll do is they'll wind the secondary and the primary, they'll just wind them on top of each other. They'll wind them at the same time. These are normally what we call E-core, which we have a magnet, we have a big chunk of metal that concentrates the field. And then they'll have a core, and these suckers are wound on top of each other. And if they wind them in the same direction, what happens is when the magnetic field goes out of the primary, it goes into the secondary. So at an instant in time, if this is positive negative, then the output of the transformer would be negative positive. Which normally in power supplies have absolutely nothing with nothing. It don't make any difference how the transformers are wound. If it's a core like this, where they wound them out here, then what they can do now is they can wind them in opposite directions. So if they wind them in opposite directions, it means when the top of this one is positive, the top of that one is positive. But we're not going to run into those that often. About the only time I see where it makes any difference is when we get into silicon control rectifiers. And when we fire those things, normally we fire them through a transformer. And when you generate a positive pulse on this side, you want a positive pulse on that side. So I'll show y'all some of those later on. But they got these little old dots on there that says, okay, if you put this one on this one, you better put your SCR on that one so it'll fire correctly. So what they're saying, since that both the dots on top, then when this is positive, this right here would be positive. That makes sense? So that would be a transformer where the polarities are given. But when this is negative, this one's negative, right? You understand? So these two polarities are going to be the same. So guys, how does this guy work? Well, notice the load is referenced to the center tap. It's not referenced to this diode or that diode, it's referenced to the center tap. So if I come in, so we've got a 12.6 volt transformer. Of course we know it's off a little bit because we're not loading it, but that's what we'll use when we calculate this. And then we'll understand our calculations are going to be a little different. So if this is 12.6 volts, then what we get between here and the center tap is we'll get what? 6.3. And then here we'll get 6.3. But when this is positive, this side down here is going to be negative. All the way across the transformer. This is 6.3, this is 6.3 left. So the center tap is, on this one, if this is positive, the center tap is negative in respect to that positive. If this is negative, then the center tap is positive in respect to the negative. Y'all understand that? So here I'm putting a positive. This is negative in respect to that. Right? You understand? Yes or no? On this one, I'm putting a what? Negative. And this is positive in respect to that. So this guy right here is on. This guy right here is what? Off. So here comes my electron flow. It's going to come out the center tap. Let's do this in a different color. Oops, that's too close to that color. So current is going to flow out here, out this piece of wire that runs up there. That represents a conductor, right? You understand that? It's going to come up here, come up through here. It's got two options to go. This guy here's off. This guy's on. What's it going to do? It's going to go back up here. It's going to flow back up here, looking for the positive. So the negative is looking for the positive. So this bottom of the resistor would be negative. The top of the resistor would be positive. I got a pulse like that. Okay, on the next alternation, this guy goes positive. This would be with respect to that. This would be positive. This would be minus in respect to that. So all I'm right now is looking at this guy right here and looking at that guy right there. This guy right here don't have a chance of being on, so it's what? It's off. This guy right here turns on. Current flows out the center tap, comes down here, comes up, comes down. Which way is it going now? Now notice, this is still what? This is still negative, this is still positive. So it's going to come down, go back to here, and it's looking for the positive. So what I got is I got this, and I just got that. And the next alternation, I'd get this. And the next alternation, I'd get that. So now we're dealing with what we call a full wave center tap transformer. Okay, guys, so let's figure out what the DC voltage will be, and then we'll take a break. So what are we putting on the input? The transformer is rated at 110 volts. It's a 12.6 volt center tap transformer. That's 110 volts, 1 amp. So we should understand our output is going to, our calculated is going to be a little lower than our true output. And why is that? Well, we're getting about 120 volts out of our receptacles, right? And we're not loading that transformer to 1 amp. So where y'all going to start? Okay, voltage peak, good. So voltage peak, we'll do secondary, would be equal to 12.6 divided by 0.707. What's that? Now what do I need to do? No, well, that's coming into play right off the bat. But we're only using 1/2. So we got one or two options. What I need to understand is that we're not getting the full 12.6 volts. We're only getting what? We're only getting what? I'm only across 1/2 of the, so only 1/2 of the transformer is working at a time. This is 6.3 volts. This is 6.3 volts. So this right here is wrong. I shouldn't have used 12 volts. I should have what? Used what? 6.3. We're only using 1/2 of the transformer at a time. So VP secondary, and this is where people mess up, is going to be equal to 6.3 divided by 0.707. What's that? Or 8.9. Here we can round to 1 decimal point, that'd be fine. Because we're approximating anyway, right? Probably need to carry it out at least 1 decimal point and round it correctly. And of course what most people do is they'll use that right there. Okay, then what am I going to do? I'm going to calculate what we call V peak out. I'm going to take 8.9 and I'm going to subtract 0.7. Now why don't we subtract 1.414? Only one diode is being used at a time. We got 8.2. Then I'm going to calculate my DC is going to be equal to 2V peak over pi. What's that? Okay, guys, y'all go take a break. We'll fire this puppy up. See what we got. Yeah, I need to pause. Yeah, thank you. So, here's our circuit. Oh, sorry, I did roll. So here's our two diodes. We've got both, if it focuses in there. The transformer, it's pretty obvious. The two red wires on the transformer are the primary. And we've got that going. So on this one we have the primary fuse. So we have an inline fuse on one of our primary leads, which really doesn't make any difference. And then to get it into my board, because I broke both my leads, by the way. We did have them soldered on the end and they would fit into the breadboard, but when we was in digital, I accidentally knocked my transformer off and it broke the wires. So what I've done is I just twisted a blue solid strand wire onto this yellow one, and then a red solid strand wire onto the other ones. Then we got them coming in. We have the anodes in different vertical lines. I don't know if you can see that or not, but this one is in this vertical line, and then this one is in this vertical line. So that means our anodes are not connected together. I don't know what it is, and I can't understand. For some reason, since these things are drawn side to side, some people see this as a parallel. Somebody in this class is going to hook these in parallel. If they're in parallel, folks, both sides are connected together. Is this cathode connected to the other cathode? Yes. Okay. Does that mean they're in parallel? No. To be in parallel, both sides have to be connected together. Is this anode connected to the other anode? Yes or no? Now, there's a transformer in between them. So no, this guy's not connected to the other anode. This guy's not connected to the anode. We just have a common connection between the cathode. But these are not in parallel. But I don't think I've ever taught solid state where somebody just don't put them suckers across each other and hook both transformer leads into the same side. So what you've done is shorted out your transformer, right? There is something between this and this. If they were in parallel, there would not be another symbol between the two anodes. These guys are not in parallel. So what I have here, of course, that's why my anodes are in different vertical lines. Can y'all see that? Here's this one right here, and here's this vertical line, and there's that one right there. If they're in different vertical lines, the vertical lines are connected together. So anything I want connected together, I hook it in the same vertical line. If I don't want something hooked together, I hook them in a different vertical line, right? Does that make sense? And then, of course, here's my resistor. It's not in it's hooked where the cathode. So there's my cathode. Everything here is in the same vertical line. We want all these connected together. And then the other side is my common. So here's my blue lead. This is the center tap for my transformer. So there's my circuit. And then, of course, what we calculated that we was going to get about 5.4 volts. So my DC output would be at the top of my resistor. What's my meter going to measure if I put it on the anode side? On the transformer side, what's it going to measure? It's going to measure 0, because it's giving me the DC average of a cycle. The DC average of a cycle is 0. This is why you got to make sure you put you know the units. Because if your meter's on DC and you put it in an AC circuit, it's going to show you there's no voltage there. Right? You understand that? So I'm going to move it over to the cathode side, the cathode side, and we're measuring 5.7 volts. We calculated 5.4, 5.7, so there's only 300 millivolts difference between our calculated and our measured. Not bad, right? Of course, we know why it's different, because it's not exactly 110 volts on the primary, and we're not pulling 1 amp out of this thing. Now, here I've got 2 scope probes, and this is what we call a dual trace oscilloscope. So we can look at 2 things. And the blue line is the AC coming in, and the yellow lines are the DC coming out. So I'm going to separate them here for a second. I'm going to move the position of channel 2. And so you see there's our AC, there's our DC. it's never going below 0. So this is DC. Here's my 0 volt reference for that channel. I've moved my 0 volt reference for the other channel down here. So what I'm going to do is put them right on top of each other again. And you see how that sucker's taking this negative alternation and steering it to the top with those diodes. Ain't that neat? So we're putting, this would be one cycle of the AC, this would be 2 cycles of the DC. So that's one thing we got to understand is your pulsating frequency. So if I was to come up here and see this on my output from the oscilloscope, what would I know right off the bat? No, it's not AC. There's my output, there's my input. What do I know? I know one of my diodes is bad. I know just like that. One of my diodes is bad. Now, this would be one reason you would get an extremely low output, right? We would get 1/2 of what we expect. If I read 1/2 of what I expect, then that usually means one of your diodes is open. That's what I did. All I did was open up one of my diodes. Here comes that. There it is. Here it is. Here, out. Yeah, out. So all I did was open up a diode. Now later on, when we filter it, it's going to be more complicated when we start getting rid of these pulses. So our ultimate goal, of course, is to get rid of these pulses. So I'm going to use a device called a capacitor. I really make sure I get the right polarity. Now watch what happens here. Now that's DC. This is pulsating DC. That's DC. This is pulsating. And of course, that's what we're going to do. So right now we're doing what we call an unfiltered, unregulated power supply. And then we're going to add a filter, and this will turn this into unregulated DC. You'll probably notice my DC voltage shoots up a lot. The 2V peak over pi formula goes out the window. So here's my DC. What do we got? I'm going to come over and put my capacitor across there. Take it off. Now, of course, what I'm doing, I'm adding more expense. So everything I add something to my circuit, I get better DC, but the power supply becomes more expensive, right? You understand? So it all depends on what you're going to run. This would run a lot of stuff, but it wouldn't run, if we ran it with a stereo, odds are we would have a humming. So then that's when we start looking at regulation. Depends on what the load requires. Resistors don't care. Resistors don't care if they get pulsating DC. They don't care if they get AC. They don't care. And they would give you the power for what voltage they see, right? You understand that? So it all depends on what you want to do. Battery chargers don't care. You ain't gonna see a battery charger with a filter on it because the battery itself acts like a filter. So if you got a battery charger and you put it on AC and you put a scope across it, you're gonna see this stuff right here. It's usually full wave. That's what it is. There's a transformer in there. That's why they're a little heavy. There'll be a transformer in there, and then you'll see pulsating DC. Now, if you hook it up to your car battery, it's going to smooth it out because your car battery acts like a filter. This is pretty neat. So what we're saying is that for every cycle of our AC, we get 2 cycles of our DC. So full wave. So we use these guys all the time. So every charger I've ever seen does the attractor. Full wave. It's usually a full wave center tap. That's what it is. So if you got a battery charger, lead acid battery charger, you put a scope across it without it hooked to the battery, this is probably what you see. Are we okay? Full wave center tap. Let's hook our motor up to it. Motor's not going to run as fast, of course, but it's going to run smoother. I should let y'all come up here and listen to the motor. A while ago, the motor had a hum. It was running fine, but it had a hum. We're not going to pick up anything on this because now it's going to be really smooth because this is getting full wave. Right? Y'all probably can't even hear it now. Well, it's running smooth as silk. So on a half wave, you're going to get that little buzz because the current is being pulsed into it, but it still averages that out. By the way, this is a problem we have with DC motors. So I'm going to come over and take my DC motor out. Oops. I removed one of my power leads. Sorry. I turned a full wave into a half wave. So you see they generate a lot of electrical noise, but also they kind of act like a filter. So notice it never goes down. You'll see it never goes down to zero anymore. Can you see that? So I'm going to take it out. I'm going to take my motor out. Okay. I did it again, guys. Pulled out the wrong way. Take my motor out. Now, of course, to be zero, it's got to come down to this. To go to zero, it's got to come down to here. I'm going to plug my meter, and you'll see this come up to here. But then it's going to add a lot of electrical noise to the system. So a DC motor can be used as a generator. You can't do that with AC motors, but with DC motors we can, which is pretty neat. So what happens is when we cut it off, it generates a voltage and fills in the gap. So DC motors kind of act like a filter, but they're not really good, and they generate a lot of noise, a lot of electrical noise, because of the switching characteristics of them, which could cause a lot of problems. Now this guy requires a center tap transformer. The problem is that center tap transformers are harder to make than, y'all know what this little sign right here means? That little sign means right here. Two portions to slash through. Now we do that for one reason. You're dealing with my computers in here. It's almost impossible to eat anything without getting crumbs. You get them all inside the keyboard, and then we have problems. Thank goodness my wife stopped using, she has a tablet now, but we had a laptop for a long time, and we were constantly vacuuming that thing out. Because people like to do what? They like to snack at the couch, right? So drinking in here is fine, but eating in here around my computers and around lab is not allowed. And we'll come in here sometimes, and they'll, for some reason, this class likes to pick up ants. I haven't seen any big bugs in here. You might run into a big old water bug down in the restroom every once in a while. But we get ants in here real easy. And the ants love crumbs, right? So, and crumbs in my keyboards are the school's keyboards. These are not mine, they're the school's. But part of the syllabus was that you're not going to mess up our equipment, the right to use policy. And plus, when you're digging into a chip bag, makes everybody hungry, right? So that's why we have break rooms and stuff, guys, and out here in the hall, but let's not eat in the classroom. You won't see me eating in the classroom. I'll eat in my office. Now, I did come in after spring break. And, somehow I left something out, and my office was packed with ants. Oh, man. It's fun.
They want to learn solid state.
Yeah, maybe. Of course, we teach a lot of other things in here. So I wasn't really sure. I don't know how to talk to ants yet. So I done forgot what book they were climbing across. That might have. So let's measure this. Oh, we did. All right. We calculated 5.2 and we measured 5.7. That's really, really good, guys. Really good. So full wave center tap, what's the big problem we have? Well, the big problem we have is people forget to do what? Divide by 2. Because the transformer is rated across the whole thing. But it's going to say 12.6 volt center tap. Which means if we take off between that center tap, then what's going to happen is we're going to divide by 2 over on the secondary side, right? Everybody understand that? Yes or no? Okay.
When you put a capacitor in,
We'll talk about capacitors later on. But what that is a filter. One of the main uses of capacitors. Now, we get capacitors where we don't want them at. And we got capacitors, anytime you bring two wires in close proximity, or if you bring a conductor to ground and it's close to ground and it's not shielded, you make a capacitor. But those are what we call stray capacitors or unwanted capacitors. But these guys have a function in life. For one thing is we can charge them and discharge them. Now they don't charge, they discharge real fast and we'll look at that. And that's what we're doing here. What we're doing is we're using the positive alternation to charge it, and then we're discharging it through the load.
I'm just curious if that secondary, DP secondary,
Sort of. Because that's what we're doing, and that's a really good call. Notice our output voltage when I put the capacitor in there was pretty much well VP. Not quite, but pretty much well VP. And we'll look at that and see why. So yeah, you can see what happens is we charge that capacitor up to VP. And then it discharges into the load. And then we charge it back up again. And what determines this is how the voltage it actually discharges to. And we'll look at the formula for that. They're really complicated. If you look at complicated for, if you look at the calculations for full wave filtered rectifiers, they give you some sure enough math. But the problem is that we're not looking for precision. We're looking for approximations, right? You understand? So calculating what we did, you can probably find all types of formulas that use sines and cosines and tangents and stuff. But just using these simple formulas, we come up and get really, really close to what we want to. My formulas. The turns ratio effect, if the turns ratio is 2 to 1, then the peak value of the rectified output voltage is half of the peak value of the primary voltage, right? You understand that? And then we have to do what? And we're only using 1/2 of that. So you got one or two things. You can divide the input voltage by the ratio and come up and then take your answer and divide it by 2. Right? You understand that? Or you can use twice the ratio, and that'll still give you the same for this power supply right here. We drew this out, so we're going to go right through it. And now you got to worry about the peak inverse voltage. What you got to understand is that one diode is going to be seeing the DC, right? You understand. The other side, it's so when the diode is reverse biased, so this guy here is going to be a plus 5 volts. This guy right here is going to be a minus VP. So if we calculated VP to be, what do we calculate? 8.9 volts. And over here we got 5.2. That diode is literally blocking what? It's blocking 8.9 plus 5.2. So it's blocking 13 volts. So the rule of thumb is just peak to peak. So, or twice this. Y'all understand that? Because this guy here is no longer dropping peak because the other side is positive in respect to that negative. And what you're trying to do is trying to figure out how much voltage the thing is going to drop. Y'all understand what I'm saying? Yes or no? So over here, this would be a minus 8.9. Over here, this would be a 5.2. What's the difference between an 8.9 and a 5.2? Well, it's sign math. So we change the sign of the subtrahend and we'd add them, right? You understand? So if I change my minus 8.9 to plus, then that's going to be plus 8.9 plus 5.2. So what we're doing is we're looking at a difference of potential. So that guy right there would have to block about 14 volts. So what we do is we just use peak to peak. Instead of peak, we use peak to peak on these full wave power supplies. Y'all understand? So on half wave, we use peak to pick our PIV. And then normally we double that. So here we would use peak to peak 12.6 peak to peak, which would be this double, right? 8.9 double. And then we would just double that. And that's what they're showing us here. So what would be our output voltage? Now calculate this for me. We got a 1 to 2 turns ratio. So what's this guy? Now notice the 1's on the left, the 2's on the right. So what does that mean? That means this guy's going to step up. This is a step up transformer. That's exactly right. RMS. Go here, Larry. So the first thing we would do, if we know our primary voltage is, if it's a step down transformer, then we would divide it by the ratio. If it's a step up transformer, then we would multiply it by the ratio. We need to get this guy. We need to do a lab. We need to get a worksheet out too. So what we got? So this would give us 50 volts across here. That would give us what? 25 volts right there. Now the other mistake people do is they use the 25 volts to calculate the DC output. That is RMS. So the first thing we're going to do is convert that to what? VP. So VP would be equal what? Everybody okay there? Okay, then what we do, we call this V peak secondary. The next thing we're going to do is calculate V peak out, which actually sets the voltage. What would that be? Subtract the diode drop. Oh, what, we okay? Yes or no? Then I calculate my DC. What's my DC? 2V peak over pi. $22.2. 1. And that's DC, guys. And we can't hook this up. We could hook it up on electronic workbench. So the big problem people have is right off the bat they want to use this. Forget to do what? Yeah, forget to convert it into VP. The next problem we have is they want to use that instead of 1/2 of that. Or one of y'all will do this. 0.7 is not as critical. It won't create a big mistake. Here we're dealing with almost 30 volts, so it wouldn't cause enough right here to be, probably wouldn't even be kind of wrong. And of course this is the math, which all y'all did. You putting output of full wave rectifier, everybody okay there? Negative supplies. All we do is do what? First the diodes. We look and see what direction the diode's pointing at. And we don't have to trace current. Here the cathodes are pointing toward the source, so this is a negative supply. All the math is the same, guys. All you need to do is just put a negative on your answer. But all the math is the same. Okay, last one, full wave bridge. Now the problem with a center tap transformer, we're going to use a center tap transformer, but normally we wouldn't use one for a bridge. A bridge uses 4 diodes. What we'll find out that diodes are a lot cheaper than center tap transformers. But we got to come up with some way where we got to use the same common on the load, right? You understand that, and do this without a center tap transformer. During the positive half cycles, 2 diodes are forward biased, which allows current to flow, and the same thing happens on the reverse cycle, the other 2. So what we're going to use here is we're going to use 4 diodes. By the way, this got the name bridge. We have a circuit that y'all probably looked at in DC. If you don't, we're going to talk about it a little bit when you take the sensors class. It's called a Wheatstone bridge, and it deals with four resistors. And normally this is the way it's drawn sometimes. So since this guy right here is drawn kind of similar to a Wheatstone bridge, this got the name as a bridge rectifier. We're not using a center tap transformer. You can, but you just don't use the center tap. Or you can use the center tap and have you can have a negative and positive supply, which is pretty neat. Huh? Yes, that's exactly. Yeah, and transformers that are not tapped are cheaper than transformers that are tapped. So notice the way this is drawn. By the way, this is one way we can draw it. But the problem is this gets hard to draw and figure out the way the diode goes. Normally I'll come up here and I'll draw it like this. And what I'll do here is I'm going to point all my diodes in the same direction. I'm going to put a wire all the way through. And this is exactly the same circuit. And then I'm going to come over here and do the same thing over here. And normally we're supposed to color those in, but a lot of people don't. And what I'm going to do is I'm going to bring my AC and we'll loop it right here. I'm going to connect one right there, and I'm going to come over here and I'm going to connect one right there. Up here, the anodes are pointing back toward the source, so this would be plus. Here, the cathodes are pointing back to the source. That'd be my DC. This is the exact same circuit. If you look right here on our AC, your AC should always see, here's my AC, it always should be an anode, cathode, and notice my AC down here, my other one sees an anode, cathode. So here, these are not in parallel. This is a lot easier to draw. But notice what happens when this is positive and this is negative. Oops, Rich, not positive, positive. So this is very popular. By the way, rectifiers are so popular, multi-rectifiers are so popular, we can get these as integrated circuits. So I can get a full-wave center tap inside it looks like a transistor, but it's not. So we'll have a device that comes up here, it'll have 3 leads on it. Usually it's in what we call a TO92 case. And usually it'll have a tab coming up here where we can hook it up to a heat sink. And now they have 3 leads coming out. Well, inside here, what they got is they got diodes pointing this way. And inside, you don't see them. They got diodes pointing that way. But all you see is what? All you see is a piece of plastic that's got 3 leads coming out. Now, we have a lot of things that use 3 leads, and we're going to find that out. But we can look inside one of these power supplies used by these desktop computers, and they'll have one of these devices in there. Normally, they'll put the diode symbols in. So we can get them common cathode, or we can get them common anode, depending on whether I'm trying to get a positive supply or negative. So, well, one thing, this is one method we use to reverse DC motors. Another thing, if I'm going to have audio is not DC. Audio is AC. So that means out in your car out there, that output of those speakers is AC. So what they're doing is they're taking the DC coming from your battery and regenerating AC. Well, the only way I can generate AC from DC is if I have a negative and positive supply. And then what we can do is we can turn on we can move our electronic circuit toward the positive, and then we can switch it off and move it toward the negative. So anytime I'm going to go from DC to AC, I got to have a negative supply. That makes sense. So yeah, anytime we're going to do that. And of course, there's all types of situations for it. So yeah, there's an inverter inside your car radio that's taking DC. Somehow it's converting it into plus and minus DC, and then it's using that plus and minus DC on your output transformers to give you what? To give you sound. And that's exactly what this device right here is doing. So we call this a function generator. Now what's neat about a function generator is that it Alabama Power in, then they run it through a power supply that somehow gives us a plus and minus DC. Right? You understand? And then now they can regenerate an AC, but now we can control the amplitude and we can control the frequency because it's done electronically. So yeah, so this guy here has a negative and positive supply in it. So I think we might have the schematics around here. I'll look for it, which is, I know we got, we've definitely got the schematics for the train. So your trainer, you got a negative supply, you got positive supplies. Well, how in the world does it do that? Well, it's got these two rectifiers, right? Are we okay? So that makes sense there? Good question. A lot of people don't understand that because most of the time you see DC, right? You say, well, what do I need AC for when my car battery only has a single power supply? And you know you can go out and buy inverters. We call them inverters. Either the small ones you plug into the cigarette lighter, your big ones you go out there and you actually clip onto your battery. And you get AC, and you don't get DC out of that sucker, you get what? AC. So if I'm going to run an AC appliance, and the only thing that's available is DC, then I've got to have a plus and minus. Somehow I got to come up with a plus and minus DC supply. So what we have here, we have plus on the top, we have minus on the bottom. Okay, so I'm going to come over here right. All I'm going to do right now, guys, is this is going to work out is I'm going to look at that plus. My motor. I'm going to come over here. That's going to put a plus there. It's going to put a plus there. This guy's going to turn off because the plus is on the cathode. This guy right here is going to turn on. Now I'm going to follow this minus over. That's going to put a minus right there, a minus right there. This guy right here is going to turn off because it's got a minus on the anode. This guy right here is going to turn on because it's got a minus on the cathode. Okay. I follow my current out just like they're doing here. So here current flows from negative to positive. It comes over here. Where does it go? Comes up, comes up. Now notice we don't have a common. So this is one thing about a full wave bridge rectifier is the common cannot be on the transformer. The transformer can't have a common on it. The common is established on the other side of the diodes, right? You understand? It's going to come up here, flow out our common, go through that piece of wire, flow up here. Which way is it going? Can't go down. That's the same potential. It's going to go up through this and turn down and go back to the positive side. So what I had is this is negative, this is positive, so we got a pulse. Now the next alternation, and by the way, we're drawing this static. You know, this starts out at 0, so the diodes are cut off, then they come on, then it follows the sine wave minus the diode drop. So notice down here, this is negative and this is positive. So I'm going to follow this negative. I'm going to put two negatives right there, negative right there. I know this guy's turned on, this guy right here is turned off because it's got a negative on the anode, right? You understand that? Okay, I'm going to follow this positive. I'm going to put my positive right there, my negative right there. My positive right there. This guy's got a positive on the cathode. It's going to do what? Turn off. This guy's got a positive on the anode. It's going to turn on. Now my current now is coming out of the other side of the transformer, negative to positive. Okay, it's going to go down through this one. It's on. It's going to go out through circuit common, come up here. Still coming negative to positive, right? Going to come back, going to looking for the positive, going to go back that way. So these guys are swapping every alternation. So what we get out is we get out this. Of course, here we don't have to deal with the center tap. Now, the only thing that changes is V peak out is going to be equal to V peak secondary minus 1.7. I'm sorry, 1.4. Because every time now we go through how many diodes? 2 diodes. Now, what's good about this one is, number one, the transformer's cheaper. If the transformer's cheaper, right, it's going to save us some money. And like I said, the diodes cost a lot less money than the transformer. So one of your big investments in a power supply, guys, is going to be your transformer. And my power supplies I built at home broke. I'll have to bring that in. They had a golf charger that went bad. A golf cart charger. And that's got a sure enough transformer in it. It's not as big as this one over here, or big as them up on the power pole. But that's what I made my power supply out of. I'll bring it in for the end of the term. No, it's regulated. Now your phone charger, these are regulated. So if you look at the back of these, this is going to give you a voltage, and you can pretty much hook that up to a resistor, and you can run. It's going to be that voltage as long as you don't exceed the current rating of the transformer. These cannot use unregulated power supplies. They got to use regulated power supplies because they're doing the stuff they're doing is so critical. They can't have that voltage varied with the load. That's why your car alternator is regulated. So it gives us out when the car's running, it gives us out a pretty constant voltage. Like I said, go out there and take your voltmeter and hook it up to your battery and turn your lights on, and you'll see the voltage of the battery drop down. Crank that sucker up, and all of a sudden you're getting about 14.3 volts, and you turn your lights on, you turn your air conditioner on, you can raise your windows, and it's going to maintain that because it's regulated. Now we don't have to have a regulator in our stereo in our car because it's getting regulated DC from the electronics, right? But inside your TV, this is Alabama Power. What's the problem with Alabama Power? Well, Alabama Power says, okay, NEC says 120 volts. Why don't they give you what you got at your house? Because they don't know what you got at your house. So what we're trying to do is come up with a method here before long that not only is the load is going to be able to vary, also the input's not going to be exactly the same. Everybody's alternator don't put out exactly the same, but it's going to be close. What do we run into these at? Well, we run into these in DC drives. You know, we run into these. We don't filter out DC drives. We do AC drives because AC drives is taking DC and turned into what? AC. So they filter that out because you can change the frequency. If you can change the frequency, if I don't filter it, I might want to turn it on while the input DC is going to 0, and that's going to screw us up. So that's filtered. But it's not regulated in a variable speed AC drive. So the application depends on what you're going to use. If all I'm going to do is run a motor, a DC motor, then this is probably what we'll use. And later on, we got a device called an SCR where we can actually control the amount of voltage going through the motor, which is pretty neat. Yeah, so this is a regulated power supply. The power supply inside this unit is a regulated power supply because anytime we do something like that, where the control has got to be so precise, it's going to be filtered and regulated. We don't regulate unless we filter. So we'll look at also another power supply called a switching power supply. These guys are harder to build, but they're more efficient for their size. These guys, you know, this is rated at 20 volts at 3.25 amps. And look at the size of it. 20 volts, 3.25 linear power supply will probably be about 4 times the size. And we'll look at that later on. Transformers can be smaller, and we'll talk about that too. Okay, guys, so what do y'all want to put on the input? Let's put 120 volts. And what's transformer? Let's say this is Or 5-to-1. So what would I get on my output way over there? No, we're talking about here. This is our output right here.
Okay.
So while y'all doing that, I'm going to go ahead and pause the lecture. Oops, wrong thing, Rich. And then we'll okay, first thing I'm going to do is I'm going to take the 120 volts. I'm going to calculate V on the secondary. So I'm going to take 120 volts and I'm going to divide it by 5. So what do we got? 24 volts. Right? Everybody okay? Then I'm going to calculate V peak secondary. I'm going to take 24 and I'm going to divide it by 0.707. What do we got? 34 volts. Okay. Then I'm going to take V peak out. I'm going to take 34 and I'm going to subtract 1.4 because we're going through 2 diodes this time. 32.6. And then I'm going to calculate my DC. That's going to be 2 VP, 2 times 32.6 divided by 5. 20.76, or 21 volts. We're almost there, right? We did work it. But we did work it. Came up with about 21 volts. Everybody okay there?
I am.
Anybody get lost along the way? 1.4, that's a common mistake. It's not a bad mistake, but it's a common mistake. Now this right here is a bad mistake right here. It's not, that's not converted to VP. And that's one of the mistakes, that's one of the common mistakes that's made. People forget to convert it to VP. My motor running. Okay, let's do it for the actual circuit. Our circuit is rated at 110 volts, right? Our transformer is rated at 110 volts. Yeah, this is the actual, it's got a ratio of 8.73 to 1. Now you got to understand the math. They say, well, how do you have 0.73 turns of a wire? You don't. It's just that if the secondary had 1,000 turns, then the primary would have 8,730, right? You understand? Which would be an equal number of turns. So we're not doing half turns or quarter turns. It's just that we're doing a ratio and it's always to 1. So we're not doing a ratio of 8,730 to 1,000, right? You understand? We would go ahead and divide those out. So this guy here has a ratio of 8.73 to 1. So it's a step-down transformer. And if it's rated, if you have the ratio, then normally you can reverse the primary and secondary. If they give you the voltage, though, you pretty much well got to leave this because of the insulation, the thickness of the insulation. That makes sense. So normally we wouldn't use this for a step-up transformer because, you know, if I came over here and put 110 volts on the what they call the secondary, then I would get over 800 volts out of the primary, and it would probably not, the insulation on the wire probably wouldn't handle By the way, commercial transformers like the one we buy, these little, sometimes they label primary and secondary voltage. So this guy here's got PRI, so that's primary voltage, and then it gives you the secondary voltage. Normally if it's and then they'll probably have the color code on what's the primary and what's the secondary on the label, right? Industrial transformers, your big transformers, your primary, your high side is labeled with H's, and then the low side of the transformer is labeled with X's. Y'all understand that? Yes or no? And most industrial transformers, you need to read up on them. They can actually be reversed, so you can use them. So they don't label them primary, secondary. They label high side and low side. Except they don't use L, because L is used for inductors, so they use X on the low side. But on commercial transformers like this one, they're probably going to label primary and secondary. And what we're trying to do, guys, we're trying to come up with what I'm going to measure over here. So we got 12.6, one answer. 10.5. Now, what you're doing, Mitchell, is you're stopping right here. So you're right. That would be 12.6 volts RMS. Not yet. No, you don't divide this by 2. This is not a center tap transformer. Y'all understand that? We divide by 2 if it's a center tap transformer. These rectifiers are across the entire, this is across the whole thing. On the other ones, each diode was only across one half of the transformer. Why would you call it artificial center tap? There's no center tap there. No. No. It's acting like a transformer. An untapped transformer. Understand? I don't know why you say birds. In fact, the commons are over here. The commons are on the diode side. They're not on the transformer side. They are on the rectifier side. So first thing I'm going to do is I'm going to calculate V peak secondary. I'm going to take 12.6. and I'm going to divide it by 0.707. When I get that answer, I'm going to minus 1.414. When I get that answer, I'm going to divide this by, I'm going to multiply it by 2, and I'm going to divide it by pi. Of course, we're not using pi. If you use the pi key on your calculator, you're wasting time. 3.14 is perfectly good for us. How long does pi go?
Never.
Yeah, it's never, well, we don't know. They hadn't found it yet. They hadn't found the end yet. It's a non-repeating fraction. It is an unreal number. A real number is a number that can be represented as a fraction, right? Not a decimal fraction, like 1/8, 1/16, or 1 over 1. An unreal number is a number that you can't represent with a fraction. So pi goes on forever. So this is not actually pi right here. 3.14 is not pi, but it's close enough for math. Yeah, I've got a PowerPoint. I've downloaded a PowerPoint where they calculated out to 1 million digits. Last time I checked, and that was, good gracious, that was probably 15, 20 years ago. Somebody already calculated out to something like 2 billion. 2 billion. I got it. See, I don't use it. I know it's 3.14159, and that's as far as I care.
Because it's given that class, somebody asked
So 12.6 divided by 0.707 minus 1.4, take that answer, so that should be inside parentheses, right? Then multiply it by 2, then divide that by pi, and what do we come up with? That looks about right. Huh? Well, let's do it one at a time and see. It's more than. Sounds like you still want to divide. Sounds like you still want to divide by 2 for some reason. We don't divide by 2. We divide by 2 on the full wave bridge center tab. So I'm going to take 12.6. First of all, we had 8.73. So first thing, and we had rated 110 volts. First of all, I'm going to find my secondary voltage. So this is going to be 110 divided by 8.73 equals 12.6 volts. Okay. Then I'm going to take the second volts, and I'm going to calculate VP, what we call VP secondary. I'm going to take 12.6, and I'm going to divide it by 0.707. 17.8. We okay so far? Okay. Then I'm going to calculate V peak, what we call V peak out. This is going to be 17.8 minus 1.4. What we got? 16.42. Then I'm going to take 2 times 16.42. It's a full wave. It's full wave, right? And I'm going to divide that by answer. Yeah, this is full wave. Half wave is V peak over pi. Full wave is 2 V peak over pi.
That's where the 2 comes from.
Not divide. A while ago you wanted to divide it. No, it's not divided by 2. It's multiplied by 2 and divided by pi. And then we come up and get what? 10.5? Close to that. We okay? Okay. So we got it up here tricking along. Here's my power supply. So here's my 4 diodes. I've got the anode cathode connected right here. These are connected together. And I went across the gap to make it easier. So here's an anode cathode connected together. I have the cathodes connected together up here and the anodes connected together right here. Okay. So there's my bridge. I'm bringing in my transformer. One of my transformers is coming into this anode cathode combination. My other side of my transformer is coming into this anode cathode combination. And here's my load right here connected to the cathodes. Now, the problem is we connect it to the cathodes, and people say, okay, that means it's a negative supply. But what we're trying to do is look what's pointing back toward the source. So the anodes are pointing back toward the source, so this is a positive supply. It should be up here running. I got my meter hooked up. I'm going to hook across my resistor. We expected 10.5, and we're measuring 11.1. Which is pretty good because we used 110. We know it's about 120, right? You understand that? Are we okay? Look at it with my oscilloscope. I have it hooked up already. There it is. I'm only looking one channel. Can't use the other channel because we don't have a common. And there's my full wave. I'm going to hook up my motor. And now it takes off because it said 10 volts instead of 5 volts, right? Nice and smooth. So over here we have Alabama Power. Over here we have DC. We got Tennessee Valley. What did it sell it?
You always say Alabama.
Yeah, we do have TV here, but most people don't. If you live in the city of Bessemer, odds are you have TV. If you pay your bill over on, what's that, Bessemer Waterworks, That's where you pay your electric bill. You have Alabama. I mean, you have Tennessee down. And they charge you, I think, $15 if you want to pay it online or something like that. That's it.
Alabama Power.
Oh, I do a debit. They never do anything extra for me. Yeah. That's pretty good power supply. Another thing, guys, you need to make sure about the size of the resistor. We're putting 10.5 volts DC on this, right? So let's make sure what size resistor we can use. So always check that. So power of the resistor is going to be equal to 10.5 squared divided by 1K. So always check that. Always. So a 100 ohm resistor is not equal to a 100 ohm. People think I can use any 100. We taught we used to teach power supply design. And then once the student built their power supply, that was their project. They did that at home. They brought it in, and then they had to do all the specifications on it to see how much current it would put out. They designed it for a certain amount of current, and then they'd see how much it would put out. And they kept saying, something's wrong with my power supply. It keeps burning up these resistors. And there wasn't nothing wrong with the power supply. They were trying to use a 1/4 watt resistor on a 30 volt supply. Okay, you'll understand that. So this is the best way to do it, is to know your power formulas. We have 3 power formulas. What are the 3 power formulas? Y'all should know. Yeah, the main one which one the other ones are developed from, is P is equal to B times I or E times I, right? Y'all understand that? Well, that's the same thing. It's a 1K. This is a different circuit, right? This is an actual circuit. So what do y'all come up? Now the other